I'd like to thank the organizers for an invitation to this wonderful place. It's my first visit to Korea, and I'm really enjoying it so far. So I want to talk about, very related to the previous talk, about Gromov-Witten invariants without mirror symmetry. So it's based on a couple of papers that I wrote in the past year, some work in progress with Halverson, Jokers, and Le Pen, and there's some parallel work independently by Shinobu Hosono. Uh, so mirror symmetry has really provided one of the most productive interactions between string theory and mathematics over the years. Just to review some history which predates the possible birth of some of the people in the room. Uh, uh, in the 80s, Dixon and Lurkov-Warner predicted that Calabi-Yau manifolds ought to come in mirror pairs. And in the late 80s, early 90s, it was found by these groups that, in fact, they do. And then in 1991, Candelas, De La Osa, Green, and Parks had a rather spectacular result showing that you can use mirror symmetry to count rational curves on Calabi-Yau manifolds. And now we say you can compute what are called genus zero Gromov-Witten invariants, which are those curve counts that they were actually doing. There were a lot of extensions of this idea that grew up from the 90s. There was an inclusion of D-branes, Koncevich's homological mirror symmetry, mirrors beyond Calabi-Yau manifolds, including the Hori-Vafa extensions to fauna varieties of various kinds, and so on. What I want to talk about here is a new approach to calculating the Kähler potential of the quantum Kähler moduli space of Calabi-Yau manifolds. It enables us to get from that Kähler potential the genus zero Gromov-Witten invariants in Calabi-Yau manifolds, which can be thought of as the two-sphere worldsheet instanton corrections for the corresponding two-dimensional conformal field theory in the infrared. It's also related to string compactifications, at least in the case of Calabi-Yau threefolds, where you get a moduli space metric, which is exact in alpha prime, although potentially subject to further G-string corrections. The traditional approach to this problem, based on this idea of mirror symmetry, was to use the mirror manifold to do the calculation. I'll review that in just a minute. There's also a direct approach, which was subsequently developed by mathematicians. First of all, giving a careful mathematical definition of the Gromov-Witten invariants. That was done by Koncevic. And then there were two mathematical proofs, one by Giventhal and the other by Lian, Liu, and Yao, of the formulas that Candelas et al. Had gotten by using the mirror. So here's a brief review of the basic mirror correspondence. If I have a Calabi-Yau target manifold of dimension D, there turn out to be two kinds of marginal operators in the nonlinear sigma model. One of them gets identified with the tangent vectors to the complex structure moduli, so they're first order variations of the complex structure, and that belongs to the group HD-1D. The other one gets identified with the complexified Kähler moduli. One of the unfortunate things about the terminology is that the words complex and Kähler occur too many times in too many combinations, okay? So I've got complex moduli, I've got Kähler moduli. Both of them are Kähler manifolds, and they have a Kähler potential describing their metric. And all of these things will be showing up. So, but anyway, thanks to non-renormalization theorems, the complex structure moduli have no quantum corrections in this 2D worldsheet theory, whereas the Kähler moduli do have corrections by instantons. And as a consequence, this mirror manifold idea, which would reverse the roles of the complex and Kähler moduli between the two mirror manifolds, is a very powerful tool for understanding these moduli spaces, and in particular for understanding their quantum corrections. So this is what led to the result I already mentioned of Candelas et al. Predicting the number of holomorphic maps of fixed degree. You just calculate with the mirror manifold. Now, to do that calculation, you have to know where you're trying to calculate. And part of the point is that the sigma model is only a good approximation when the volume is large. So you should go in this moduli space of Kähler parameters to a large radius limit point. I put the bar there to indicate a compactification. This large point is really outside the moduli space. And if you want to correctly describe the moduli space, you have to take into account integral shifts of the B field, which are what were used to complexify the Kähler classes. So typically, you can write a coordinate in terms of a basis of this space H11 that characterize the marginal operators. The corresponding coordinates are TJs, but then you should exponentiate those coordinates in order to naturally take into account the integral shifts of the B field. This is something I talked about in strings 93. This tells you how old the subject is. So those of you who were there at my talk 20 years ago, you might have heard a little more about it. So there are various physical quantities which can be computed in terms of this moduli space, and they typically will have a classical term which is directly expressed in terms of geometric properties of this intersection, the intersection ring structure on the even cohomology. For example, you might have a d-fold intersection pairing, which is the classical term in a d-fold correlation function on this particular variety. So if we want to use the mirror idea to do computations, we have to find corresponding large complex structure limit points in the compactified moduli space there. There will be coordinates near a large complex structure limit point, and what you really have to do in the basic mirror correspondence is make the logarithms of those natural coordinates correspond to the coordinates that would be most natural on the Kähler classes, and the structure of those logarithms, fortunately, was already available through mathematical study of the behavior of Hot structures, the way that the cohomology of X behaves when the complex structure acquires singularities. Now, the topic of today is metrics on moduli spaces, and actually the metric on the complex structure moduli space was written down in the early days of the study of Calabi-Yau manifolds by Tian and Todorov, who were proving that all first order variations of complex structure really can be extended to all orders. And in order to do that, they wrote an explicit Kähler metric on the moduli space as a very simple form. All you have to do is take the unique holomorphic top degree form capital omega, which is depending on parameters little z, wedge it with its complex conjugate and integrate over the manifold, and then that as a function of z and z bar is naturally, when you took the complex conjugate, is now depending on z bar. That describes the Kähler potential of a metric on the moduli space. And if you use a basis for the cycles over which you can integrate this top degree form, choose a symplectic basis, then you can easily rewrite this in terms of those so-called period integrals, the integrals of the top degree form over the cycles. So near this large complex structure limit, as already mentioned, there's a kind of logarithmic behavior of the explicit period integrals, and you can in fact find those logarithms showing up in this Kähler potential. So the Kähler potential is a real function. The logarithms had some periodicity in their complex, in their argument, right, in the imaginary part, but the combination that's used to make the Kähler potential still shows the logarithmic behavior near the limit point, and because of that logarithmic behavior, you can learn how to make the correspondence sort of precise. Now, this was part of the original Candelas et al. Argument, but it's not a part of the argument that was typically generalized in subsequent studies. Typically, people were focusing on comparing and extracting information about Yukawa 3-point functions, or in the case of Calabi-Yau manifolds of higher dimension, d-point functions. But in fact, equivalent information can be gotten by looking at this Kähler potential, which is what we're doing now. So if you ask the question, what is the general form of the metric on the back now on the Kähler moduli space side, just by analyzing the two-dimensional field theory from a perturbative point of view, you discover that the general form has to be based on this intersection property. So you can take a polynomial of arbitrary degree, something wrong with my indices there on the summation, you can take a polynomial of arbitrary degree weighted by an appropriate cohomology class, which kind of serves as a coefficient in here. That cohomology class is unknown just from this sort of general analysis, but there's some cohomology class which will account for perturbative corrections in addition to a classical term, which is the top degree, the degree D term in this thing. And then I've just indicated by big O of e to the minus t, the instanton corrections. Those are the things we really want to extract, but in order to extract them, we need to know about the asymptotic behavior first so that we can sort of get our hands on the not exponentially suppressed corrections by making a complete calculation. So I'm making a calculation of a Kähler potential. It's only well defined up to adding the norm of a holomorphic function. And in particular, if you choose a different omega, this was a remark about the original Tian-Todorov construction, you can choose the omega arbitrarily without changing the result for the actual metric. And as a result, you can find these preferred coordinates, the ones that allow you to compare directly between the two sides of the mirror picture, and that's what lets you eventually read off through some series expansion the values of Gromov-Witten invariants. So here's the proposal, as mentioned in the previous talk. If we have a Calabi-Yau manifold whose 2D field theory has a Lagrangian ultraviolet description so that we can write it as a gauge linear sigma model with n equal 2, 2 supersymmetry, if you calculate the partition function of that ultraviolet theory on the 2-sphere, then the answer that you get is an answer about the Kähler moduli space of the infrared conformal field theory. It's an ultraviolet calculation of some quantity which is not changing. And our proposal was, which was subsequently argued to be correct by Lee and Gomez, our proposal was that that 2-sphere partition function is e to the minus Kähler potential. So in fact, it was motivated by observing the form of the answer of the partition function, and then now we have some nice arguments which sort of back it up. But one remarkable feature of the answer that they calculated for this partition function was that it depends only, although it's this is not a calculation in a twisted in an A twist or a B twist. And so you might have expected that whatever the answer was depended on both Kähler and complex structure moduli, but as has been argued, it does depend on how the supersymmetry algebra was modified to be lifted to the sphere, to the 2-sphere, and it ends up in the choices that have been made, it ends up selecting the Kähler moduli rather than the complex moduli. So I just want to remark that this proposal about the Kähler moduli is the latest in a series of results over the years. So in Abelian GLSM cases, really starting from Witten's original paper and then expanded upon by Plesser and myself, you can compute instanton corrections very explicitly, although not quite in the correct coordinates to immediately read off the Gromov-Witten invariants. You can also find the precise form of the moduli space. So here's a picture of a case that Plesser and I did, the P11222 case, where there's some picture of the singular locus of the moduli space. And in fact, the mathematical proofs of given Liang, Liu, Yao were based on closely related considerations, manipulations of essentially instanton sums or mathematical analogs thereof, which were able to give the mathematical proof. And those techniques were extended further to give hypothetical predictions for Gromov-Witten invariants in a broader variety of cases that aren't necessarily confined to Abelian GLSMs, including the case that I'll describe in some detail later. So I'll come back to that remark in just a moment. Just to illustrate the kind of complexities involved, particularly when proceeding to Calabi-Yau manifolds beyond dimension 3, which is the subject of the forthcoming paper. If I start with the standard projective hypersurface of degree d+2 in CP d+1, it has a complexified Kähler moduli space, where I take the parameter to live inside H2XC, whose imaginary part is a Kähler class, the real part I'm thinking of as the B field. I exponentiate that to take into account the periodicity of the B field. Or I can look at the mirror hypersurface, which begins life inside of a quotient of projective space by the Green-Plesser construction. That's the YD plus 2 bar. That has singularities, so you resolve the singularities to get the hypersurface mirror. And the ordinary or complex structure moduli space, for that case, the parameter conventionally is, I followed the conventional literature in originally naming the parameter, but that parameter Z is a better one for comparing with the mirror. And to identify the two, you have to know something about the periods in the case of the mirror variety, and compare the behavior of the periods on one side, the monodromy of the periods to the multivaluedness given by the B field variation on the other side. I have no idea what time I started. Do you know what time I started? How much? Oh, 15 minutes, okay. So, if I identify a particular cycle, gamma, then, and if I somehow manage to explicitly figure out the value of that period, then I can take the limit as Z goes to 0 and do some kind of series expansion. That's one approach to studying these periods and making the correspondence work. Or I could try by differentiating under the integral sign to learn about the differential operators which annihilate the periods, and those turn out to be closely related to the intersection ring of the mirror variety, and the solutions can then be constructed by power series methods. Comparing the two turns out to be important for getting a handle on the asymptotics that I was talking about before. So for the first one, you can explicitly integrate a kind of residue over a real torus inside of the complex torus that sits inside of CPD plus 1. So that gives a specific torus to integrate over, and one checks that that integral is well behaved in the large complex structure limit. And there's an expression which I unfortunately did not write the slide for, which explicitly evaluates this in terms of gamma functions. On the other hand, you can write down the differential operator. In the case of the quintic, here it is. And you can use standard power series methods, the so-called method of Frobenius, to solve for series solutions of this equation. There's the nice single-valued series solution, but we also need information about the other ones, and there's a nice trick, again, due to Frobenius, to put in some other value, alpha, and look for a series expansion in z to the alpha plus n over n. If you apply the differential operator, you discover that alpha to the fourth has to vanish for this to make sense. And okay, that's okay. I can work. I'm an algebraic geometer. I can work in the ring C of alpha mod alpha to the fourth. It really just means that you do all your computations in the naivest possible way, and every time you see alpha to the fourth, you set it equal to 0. So no problem. That's an algorithm for finding the solutions, and you get multi-valued solutions in that way. You can expand z to the alpha in terms of 1 plus alpha log z plus half alpha squared log z squared plus a 6 alpha cubed log z cubed, and then it stops because alpha to the fourth is equal to 0. So you get all 4 solutions in that way. And the key formula, which I didn't write down, although should have, relates the power series, the explicit calculation here in terms of a residue on a torus integral to the series solution like this. But it has a complete parallel in what we calculate for ZS2. So I'll come to that in just a moment. So as has been stated, what we have now is a really nice technique for evaluating the partition function on a two-sphere if there is an ultraviolet description of the theory in the form of this gauge linear sigma model. So to write down a gauge linear sigma model, I have to tell you a gauge group. I have to tell you some chiral superfields which transform under a representation of that gauge group, and I have to give you a gauge invariant superpotential, typically a polynomial in those fields. And the Lagrangian is this very standard-looking Lagrangian, which also involves a twisted superpotential. In these theories, that's taken to be r plus I theta, including the Fi term and a theta angle, which is paired with it in the supersymmetric version, where the sigma is a twisted chiral field strength of the vector superfield for this gauge theory. So if I want to do it for the Calabi-Yau hypersurface that I had on the last couple of slides, this construction is pretty well known. I take just U1 as the gauge group. I take D plus 2 fields of charge 1 each, and another field traditionally called P, whose charge is minus D minus 2. The sum of all the charges is therefore 0. That's an important condition for a conformal field theory in the infrared. And there's a nice superpotential in which I just take my previous homogeneous polynomial of degree D plus 2, evaluate it on those superfields phi, and multiply it by P, making it gauge invariant. And now there's a very familiar analysis which says that if my Fi term is sufficiently positive, then the D term equations, together with the gauge invariance, produce as a geometric space a bundle over CPD plus 1, whose fiber coordinate is P. And the F terms then restrict us to the 0 section of that bundle, which in other words fixes P to 0, as well as setting that polynomial F to be 0. So I get back to the Calabi-Yau manifold that I started with. I should say that it's still open, so far as I know, whether every Calabi-Yau manifold can be recovered as the infrared limit of some gauge linear sigma model. It certainly faults for abelian gauge linear sigma models, but we now have an interesting class of examples of non-abelian ones where we're able to do manipulations, and it's not clear whether that class is going to cover all Calabi-Yau manifolds or not. It would be great if it did. On the other hand, if it doesn't, there will be an interesting task to try to learn about the 2D conformal field theories that have those sigma models as their targets with no obvious ultraviolet completion for the sigma model. Okay, so now I get down to the meat of the story. I'll use the formulas from the previous lecture, and actually I've just selected out one term of this formula because to get going, I'm interested in knowing about the perturbative part of this two-sphere partition function. So the part which, in terms of the variables, is just going to look polynomial in terms of the variable t, which is appearing there. So that's not the complete thing. The whole thing is a sum, but that's the polynomial part. And it can be rewritten in this nice form where n is supposed to be d plus 2. I apologize. I forgot to change that line on the slide. All the rest of the n's are d plus 2's. And we end up with a perturbative expression that involves various gamma functions. And now I've substituted in H, which is the hyperplane class, and I'm doing my manipulations in the intersection ring of the projective space. So I have a nice expression, and the reason it's polynomial, by the way, is that e to the h is just, again, that finite sum, 1 plus h squared over 2 plus h cubed over 3, because h to the fourth is equal to, plus dot dot dot. In the case of a hypersurface of a Calabi-Yau d-fold, h to the d plus 1 will be equal to 0, so that's only a finite sum. And then this slightly complicated expression is picking out the contribution to the perturbative part of the thing. And I can write it very simply as a ratio of something called the complex gamma hat class, gamma hat c of x divided by its complex conjugate. And this is a multiplicative characteristic class which is based on a power series expansion for the gamma function. So characteristic classes generally are based, multiplicative characteristic classes, you get one for every possible power series expansion. And this is a natural one that shows up from this formula, which I forgot, as I said, to put in the other slide. It's the same formula that you get comparing the answer to the explicit integral over the real torus with the method of Frobenius version of the integral that involved the alpha. So either way, you arrive at this gamma class, and this use of this gamma class to interpolate between the two was done in the case of d-point correlation functions by Liebgober in 1998, and was emphasized recently by Kontsevich as part of mirror symmetry. I'll come to that part of the story in just a minute. But anyway, there's a very explicit way of getting your hands on the perturbative correction. And for Calabi-Yau threefold, this was already in the Candelas et al. Paper. There's a term involving the second Chern class, and there's a term involving the third Chern class times zeta of 3 over 2 pi quantity cubed. That was identified as being a very natural perturbative contribution to the answer, which is why, well, and is necessary because it shows up in the asymptotics in order to extract the answer that we want to be able to get. So you can actually nail down all those coefficients, alpha j, by a similar sort of consideration. In fact, there are enough examples that are simple enough in this form that you can conclude that the gamma class formulation is the general one and gives those coefficients alpha j in the perturbative formula that I had before. So the version of the gamma class which has been introduced in the mirror symmetry literature before, about 5 years ago, was a proposal by Iritani and Katsarkov-Kontsevich-Pantev to modify what's usually taken as the identification of K-theory with cohomology to describe either the integral structure in mirror symmetry or to describe D-brane charges, namely to multiply the Chern character by the square root of the Todd class, to replace that square root of Todd class by the complex gamma class. And it has the nice property that the complex gamma class times its complex conjugate for Calabi-Yau's again recovers the Todd class, so that you get the similar properties with respect to the Hertzsprung-Riemann-Roch theorem and the Mukai pairing, all sorts of stuff which I don't have time to talk about today. There's a much more direct piece of evidence for this proposal in terms of the Hori-Romo forthcoming work that Sangjay already mentioned. They're computing the partition function on a disk and on a cylinder, and they end up with this result rather directly. So I want to conclude with an example where we were actually able to kind of replicate the original Candelas et al. Type computations and count some rational curves on a Calabi-Yau threefold. And the one that we took has a GLSM description. I've described it here. There's a U1 cross U2 group. I've got certain representations of the group and a superpotential. And then there's a little analysis which tells you that at low energy, you get a geometric phase. I missed a piece of the slide, which is simply described as the set of points where a certain 4x4 matrix has rank 2. So this is a set of points in P7 where some 4x4 matrix with linear entries has rank 2. It was supposed to be on this slide. It got left off. And by using the considerations I've just described and then to normalize the coordinates and then extracting instanton contributions, you end up with the following table. So these are numbers which hadn't been calculated before. There, as I mentioned, some extensions of the Giventhal method lead to another approach to calculating these numbers, but also one which doesn't have a mathematical proof as being the actual correct numbers. And this is a case with 2 generators of H11, which is why there are 2 numbers there. And the natural generators are edges of the Kähler cone where 56 curves are contracted to nodes, and that's what the 56s are on the table. It's also true that after you contract those 56 curves to nodes, you can smooth the resulting curve into a complete intersection in a toric variety, and as a result, the instanton numbers are known in that case, and those are given by the sums of the columns in this result. So each column has to terminate after a finite number of steps, and the sum has to equal a known number, and that's true. Moreover, the columns, if you notice, are all symmetric about the middle. So there's a middle largest number, and the column is symmetric about that, and that's a consequence of the geometric fact that the flop of this Calabi-Yau manifold on those 56 curves is again isomorphic to the same Calabi-Yau manifold. So there's various indirect checks, and the numbers 56 and 192 we also verified geometrically. So this is the old style stuff from 20 years ago where we didn't understand the phenomenon too well, so we calculated very hard and sort of checked that things worked. This is a case where we don't have a mirror, so we had to make similar checks. Okay, so let me just conclude. I've talked about how the partition function calculates the exact Kähler potential of the quantum Kähler moduli space. Another thing we've explored, which I didn't have time to cover today, is that the phase structure of the moduli space, the Kähler moduli space, which had been discussed a lot in the past, can be analyzed using this formalism, and we learned some new and interesting things. We've calculated the genus 0 Gromov-Witten invariants, but we have no idea what to do about other genus at the moment. It would be great to extend this to other genus. And like Sanjay, I'm very optimistic that we can use the insights gained from this calculation to make progress on finding mirror manifolds in the non-abelian GLSM cases where they're not currently known. So I'll stop there.
Any questions? Yeah. Over there.
The sense in which the mirror symmetry exists in general Calabi, we know cannot exist for arbitrary Calabia. For example, the rigid Calabias cannot have mirror. But even in those cases, we have a mirror-like geometry which allows you to compute for the mirror, for the Gromov-Witten invariants and so forth. The same is true for the non-abelian cases. Why do you expect there's anything better than that? In other words, we know in the non-abelian case to do the analog of the Landau-Ginzburg models, which give you a computation for the mirror for the quantities of Gromov-Witten invariants, and one would not expect that the general case is any better than the rigid case. Why should you expect the actual mirror?
Well, so let's see. So I guess the precise statement I would make is that any time you have a limit point in the complex structure moduli space with the correct monodromy properties, you should expect a mirror. So the rigid one escapes having a mirror for that reason. There aren't any moduli for it to have that limit point. And if I accept that as the sort of refinement of what the mirror correspondence is giving me, then I should expect for any Calabi-Yau manifold to be able to find geometric mirrors. The Landau-Ginzburg mirrors are really useful for making calculations, but I should also expect to find geometric mirrors.
But for the purpose of computation, genus 0 or higher, the Landau-Ginzburg is as good as any other description. So in other words, if the point of mirror symmetry is to try to give you another description which allows you to compute, the Landau-Ginzburg description, which are available for non-abelian ones as well, are as good. So the point of mirror symmetry, and including description of the branes and all that, can be done in that context. So I think the notion of mirror symmetry should be a little broader viewed, not just in terms of a geometric manifold, but in terms of a simpler description LOB model.
Right, so you're proposing to describe certain physical features, all of which belong to the topological theory rather than the physical theory. And what I'm suggesting is that...
No, I'm not saying that. Landau-Ginzburg theories is a full theory. You can take the infrared limit of that theory, it gives you a complete theory. So you take the Landau-Ginzburg description, it gives you not only the Gromov-Witten invariant, but the full theory. It doesn't have to be geometric theory, it has a quantum field theory, and it is.
So I don't know that the Landau-Ginzburg description exists for every Calabi-Yau manifold, because I don't know that every Calabi-Yau manifold has some kind of GLSM realization. So if I take a random Calabi-Yau manifold without a known GLSM realization, then I don't necessarily
know. For the non-abelian example.
For the non-abelian GLSMs, there are Landau-Ginzburg descriptions for some class of them. I'm not sure that the Landau-Ginzburg mirrors exist for the full class of non-abelian GLSMs. We could talk about that later.
Yeah.
So actually, perhaps this question should have been asked at the end of the talk by Sonjin. So this is actually a question to both of you. So unlike the case of correlation function, I think the partition function may have some computational partition function may have some ambiguity in terms of normalization of functional integral and also maybe possible counterterms. So in order for those ambiguity not to affect this computation, there ought to be some kind of theorem, that vanishing theorem of some kind that prohibit such possible counterterms. And is that known?
I would like to hand that question. Both of us say no.
Any more comment? Questions? Okay, if not, then thanks, speaker, again.